So again, one of the first structures I want to look at is this whole tharsis region of Mars. So again, we're back to this issue of having a planet with no oceans to orient ourselves, but again, tharsis is this area of large volcanoes and uplifted terrain in the Western Hemisphere. So we're talking about, Olympus Mons here, the Tharsis Montes volcanoes, the large shield volcano that's up here, on all of this kind of volcanic province that's in this area. It's a little bit clearer on the Mars MOLA map that is displaying the different elevations in color. So, you can kind of see tharsis here as this huge pimple or wart on the side of Mars. So, what would be potentially the processes that you could think of based on an understanding of what's going on the Earth that would result in this high elevation area sticking on the side of the planet? What are possibilities?
Well, there are no plate tectonics, but we also have hot spots like Hawaii.
Okay.
Lava rising up from the crust and forming islands in the middle of the ocean.
So, could it be the result of some hotspot over the long history of Mars leading to the upwelling of this area? Plate tectonics would be an option for producing this kind of structure. If I hadn't already told you that we really don't have much evidence for plate tectonics, how would plate tectonics result in this kind of elevated region?
One plate would slide over the other plate.
One plate sliding over the other plate. So we have similar kinds of regions on the Earth. The whole Tibetan Plateau is this hugely elevated area of continental crust. The result of essentially India slamming up into Asia and causing a massive uplift of that continental plate. But that's not going to be what's happening here on Mars. So let's focus on this idea of hotspots and what some of the ramifications of that are. Okay. Again, just some other views of this tharsis region, more presented on a globe structure. So, in terms of the Tharsis Montes, the equator runs basically through Olympus Mons there, the middle volcano. Olympus Mons, this huge, tall volcano, is a little bit north of the equator. Okay. So this is not Hawaii. This is actually Antarctica, but it is dealing with this idea of mantle plumes. How many of you are familiar with lava lamps? How many of you ever owned a lava lamp? Yeah, I did. I owned one when they were new. This is an example of, again, these convection processes. So what's going on in the lava lamp to make it?
The heat is making it rise, and when it cools down, it starts to sink.
Okay. So there are two phases in the lava lamp. There's the water, and there is the waxy organic material. Okay. And the water is pretty much just colored water. And the lava has been carefully selected to have a density that is just very close to the density of water. When the material is not heated, it's a little bit denser than water, so what happens to the lava when you turn the lava lamp off? It all sinks, okay? So then you turn the lava lamp on, and what's actually doing the heating? There's a light bulb down the base there, and that incandescent light bulb is putting out a lot of heat. It's heating up this polymer, and what happens to the density of that polymer as it heats up? Density decreases, it gets lighter than water, and the warmed material then rises up through the water column because it's less dense. And then, of course, what happens to the temperature of those blobs when they get to the top? They cool off. When they cool off, they become dense again, and they sink. And so that's essentially the idea of what's going on with a convection movement, a convection current. You've got bulk movement of material driven by these temperature differences, and the material rises through the water because at that point it's denser than the surrounding materials. And so with the mantle plume, you have essentially the same thing going on. You have localized heating of mantle material leading to, if it melts enough, it's going to lead to an actual magma chamber that will, if there's enough pressure on it, try to make its way to the surface and, erupt volcanically. But underlying all of that is this much larger process of having this mantle plume, this large batch of less dense material that is rising up through the surrounding mantle material. And we see these in a lot of volcanic regions. Hawaiian Islands are a good example. These areas in Antarctica where you've got these volcanic provinces are part of the same thing here. Okay, so in the case of the Hawaiian Islands, you've got this hot spot that has remained in the same place for long periods of time, leading to the continual rise of hot mantle material and actual flows of magma. And what's happening is that the Pacific Plate crust, the Pacific Plate part of the crust, is moving along over that hot spot. And it's moving here from east to west. Well, from southeast to northwest, really. So, if you look at the Hawaiian Islands themselves, which of the islands, anyone been to Hawaii? I've not. But Hawaii, the main island, is the oldest or youngest of these islands? How many say youngest? How many say oldest? It's oldest. Okay. I mean, it's youngest. Right. So this is the current area where that is directly over the mantle plume. So this is where the magma is coming up. This is where the new islands are being formed. What will happen to the island of Hawaii as the plate continues to move? It's eventually going to move off the hot spot, right? So what will happen to volcanic activity? It'll decrease. And then what will happen to the island over time? What? It'll keep moving to the northwest, and as it's moving to the northwest, it's not sinking, it's eroding. So there's rainfall, there's material being washed off the island, there's weathering of the minerals and so forth. Jim?
So the other islands originally were much taller too, but
yes. The older islands of the Hawaiian chain had their time in the sun when they were over the hot spot, when they were being built up. Then they got shoved off by the plate movement, and volcanic activity either declined in the case of the not quite so young islands, or stopped altogether. And then once that island building activity stops, erosion takes over and the islands gradually wear away. If you look further and further northwest, you can see not islands, but basically undersea seamounts where the islands that used to be, large and so forth, have eroded away to the point where they're not really islands anymore. And in about, a couple million years, the plate will have moved further off. The island of Hawaii will become quiescent, and there will be new areas of island building happening. Okay, so that's how it's happening here on the Earth with these two examples. We've got the mantle plume in Antarctica. We've got the Hawaiian Islands showing up as a chain of volcanic islands because of this plate tectonics movement over the mantle plume or the hot spot. Why then did Olympus Mons get so large?
Since there's no plate tectonics, the hotspot just continue to rise over
Yeah.
one.
So essentially imagine the main island of Hawaii sitting over the hot spot for 3 billion years. Okay. You're going to tend to build up a very large shield volcano, and that's essentially what Olympus Mons is. Probably, if you looked at Olympus Mons, it was probably starting to be developed during the Noachian era way back when, throughout the Hesperian, and it's quite likely that there is still active volcanism, not in terms of, gee, if you go there today, you're going to find fresh lava flow, but at any point there could be fresh eruptions. Clearly this area is not dead. You had a question?
I was actually just going to ask about Hawaii. Like, is there any specific reason why it moves northwest, or is it just happen to be?
Well, that's the movement of the plate
Like it just
itself.
happens to be that plate
Yep.
moves to the northwest. It's not like anything to do.
Well, all of the plate movements on the Earth are driven by these convection cells in the underlying mantle. And so each of the 2 to 3 dozen plates that have been identified have their own directions that they're moving. So in the case of the plate that India is sitting on, it's moving very rapidly north, which is why it ran into Asia and basically created the Himalayas and the Tibetan Plateau and so forth. I used to be in Southern California, and there we've got interesting movements of plate boundaries against each other. So they're not running into each other, but the Pacific plate is moving off to the north compared to the continental plate. And so, San Diego and Baja California will at some point in the future be up adjacent to Washington State, which leads to a lot of earthquake activity and other kind of fun stuff. But yeah, each of these plates has their own direction that they're being driven by all of this movement that's going on underneath. One last point on this, and we'll have to leave the other mini presentations till later. It's quite curious, perhaps, to realize that this huge wart on the side of the planet pretty much straddles the equator. So is that just coincidence, or is there something that resulted in that location? So you can see there, Pavonis Mons is pretty much right smack on the equator, and I don't know if you're familiar with space elevator technology, but if we ever have a space elevator on Mars, that would be the prime place to put it, so that we wouldn't have to use rockets to get up and down. We would just have a cable from orbit down to the planet that we could send cable cars up and down.
Why not Olympus Mons?
Because it's not on the equator. The orbital station for the space elevator needs to be in geosynchronous orbit over the same planet, same point on the planet. You can do that over the equator, but you can't do it if you're not on the equator. We'll go into the mechanics of all this. There are some articles we could look at, but there's no time. But what is likely to have happened is this hotspot could have been somewhere else at other than the equator. You know, it's thought that it was actually initial development of tharsis was up in the northern hemisphere. But if you've got a spinning ball with a big wad of gum on the side of it, just natural centrifugal forces would tend to move that lump of extra material down to an equatorial position in order to conserve angular momentum and so forth. So it's quite likely that the development of this huge shield on the side of Mars actually played the role of tipping Mars over from what it used to be on its axis to a new axis of rotation, where this whole big tharsis region was now on the equator, which is a much more stable configuration for the spinning planet.
I was going to ask if that was true, would it keep tilting until Olympus Mons was on the equator?
If you look,
Or the other three, like,
I mean, if you look at the mass of the Tharsis province, you know, Olympus Mons is a big part of it, but it's probably at the point where it is balanced between northern and southern hemisphere at this point. So Olympus Mons by itself is not going to continue to tip Mars further over. Okay. So again, on Monday, we'll meet here. We'll defer any more of these just so stories about these different structures on Mars. We'll talk a little bit about rocks, and then we'll go down to the geology lab. And then Tuesday evening, 7 o'clock, in the PepsiCo Theater for the plenary session.